I'm going to briefly demonstrate the use of an interactive simulation that shows partial pressures of binary system where we have both ideal and non-ideal behavior. So this simulation is located in the LearnChemE site, and here's the link to that site. Simulation allows us to change the saturation pressure of pure component A. That's this intersection here on the left side of the graph, and on the right side is saturation pressure of B, which we can change with this slider. And then we can look at deviations from ideal behavior. So the dashed lines correspond to ideal behavior, and here we have deviations from positive deviations. So the pressure above the mixture is higher than Raoult's law. Raoult's law is predicted by the dashed line, and this dashed line is contributed by two species, partial pressures. The system for non-ideal is because we have an activity coefficient. So I've indicated equations when we have non-ideal behavior. So partial pressure of A is proportional to the mole fraction, saturation pressure, and the activity coefficient accounts for non-ideal behavior. The activity coefficient is 1 when we have Raoult's law. So equivalent expression for B, and so the total pressure is the sum of these two partial pressures. Look at the interactive simulation. So here's the simulation. We have directions that briefly describe how to use the simulation and the equations. The details then show the equations, some of which I just showed you. Here we're looking at Raoult's law because there's no deviation from ideal. You can have negative deviations and the pressure is lower above the mixture because of attractive interactions in the liquid phase that are stronger for the mixture than for pure components. And then positive deviations. If positive deviations are large enough, we have a maximum. And that corresponds to an azeotrope. And you can see the contributions from the two components that make up this behavior. If I check this box here, then we show these red dashed lines, and this is Henry's law. So the Henry's law constant is the intersection. It's off scale. This is Henry's law for component B, only applies at low concentrations. And here's Henry's law for component A, again at low concentrations of A. So hopefully this type of simulation helps you visualize a little better Raoult's law and deviation from Raoult's law.